Inside every single digital device you own, your phone, your laptop, everything, there's this constant, frantic need to hold on to information, even if it's just for a tiny fraction of a second. Well, that's the job of the register, and it's one of the most fundamental building blocks of all computing. So today, we're going to dive into exactly how they work and why they're so absolutely crucial for everything your computer does.
All right, so we've talked about the flip-flop, that amazing little device that can hold on to a single 1 or a single 0, which is great, but that's just one tiny piece of the puzzle, right? How in the world do we get from storing just one bit to storing a whole chunk of data, like the number 8, or say the letter A, which needs 8 bits all on its own?
And the answer is, well, it's brilliantly simple. We get the register. You just take a bunch of flip-flops and you group them together. If you need to store an 8-bit word, guess what? Use a register made of 8 flip-flops. The key is that they all share a common clock, which means they all capture their data at the exact same instant.
Okay, here's a super simple way to think about it. Picture a row of light switches. You can walk up and set them all to a specific pattern of on and off, and they'll just hold that pattern for you. That's a register. And when you load all those bits at the exact same time, bam, on one single tick of the clock, that's called parallel loading. It is by far the fastest way to get data into storage.
So, storing data in one spot? Check. But the real magic, the stuff that makes modern tech possible, happens when you need to move that data around. And that brings us to a very special, incredibly useful type of register.
I mean, think about it. Sending 8 bits of data in parallel means you need 8 separate wires. Now, inside a tiny chip, that's okay. But what if you need to send data across a room, or even across the country? Running 8 or 16 or 32 cables is super expensive and really complicated. So what if? What if you only had one wire? How could you possibly send all that information down a single path?
And this is where the shift register comes in. It's basically a standard register, but with a superpower. It can move its stored bits one position at a time, either to the left or to the right, every single time the clock ticks.
The best way to picture this is like an old-school bucket brigade, passing water down a line. On each clock pulse, tick, every flip-flop passes its bit to its neighbor. This lets a whole sequence of bits march into the register one at a time, or march out of it onto that one single wire.
Okay, let's actually see this in action. It'll make so much more sense. We've got a simple 4-bit shift register here, and we're going to feed it a stream of bits, one by one. Our first input bit is going to be a 1. Now watch what happens. All right, on the very first clock pulse, tick, our input 1 gets loaded into that first flip-flop on the left. The rest of the register, for now, we'll just say it's full of zeros. See? Simple enough.
Okay, now let's say the next input bit is a 0. On the second clock pulse, tick, the new 0 comes into that first spot. And what happens to our original 1? It gets shifted one spot to the right. You see how it's just moving right down the line? And on clock pulse 3, tick, a new 1 comes in. It pushes the 0 over, and that 0 pushes our original 1 over again. With every single pulse, the entire pattern just shifts one position to the right, making room for the new bit at the front.
Okay, so that's a neat little trick, right? Shifting bits around. But why is this one of the most important concepts in all of digital communication? Let's get to the big payoff. So this gets us to a really, really important trade-off in all of digital design. Parallel transfer is blazingly fast. All the bits show up at once. But it's expensive and clunky. You need a wire for every single bit. Serial transfer, on the other hand, is slower because the bits have to arrive one by one, but it is incredibly economical and simple. This is the core principle behind tech you use every single day, like USB and Ethernet and SATA. They all depend on shift registers to send enormous amounts of data over just a handful of wires.
And the whole process, when you see it laid out, it's so elegant. Check it out. On the transmitting end, you take your data and you load it all at once, in parallel, into a shift register. Then you just clock it and it shifts the data out one bit at a time onto that single wire. Then, on the receiving end, another shift register is there to catch those bits one by one. Once it's full, you can read the entire chunk of data out in parallel again. You've just converted parallel to serial and back again and sent a whole word of data over one wire.
So, that's the concept. But how do engineers actually design these things today? I mean, they're not sitting there drawing out every single flip-flop by hand anymore. Instead, they describe the behavior of the circuit using a special kind of language.
These are called hardware description languages, or HDLs for short. Verilog is one of the big ones. And with an HDL, you can describe an incredibly complex circuit, like our shift register, in just a few simple lines of code.
For instance, get this. This single line of Verilog code describes that entire right shift operation we just animated. Now, I know it looks a little cryptic at first glance, but I promise it's actually super logical once you see what it's doing.
Let's just break it down real quick. That little arrow thingy just means our register, A_par, is going to get this new value. Simple. The real magic is in those curly brackets. That's just Verilog's way of saying, hey, let's stick these bits together. So we're taking our new input bit, MSB in, and we're sticking it right next to the first 3 bits of whatever was already in the register. That's it.
So really, all that fancy-looking line of code is saying is this. The register's new value is the new input bit, followed by the first 3 bits of its old value. The 4th bit, it just falls off the end. It gets discarded. It perfectly and very concisely describes that shift operation we saw. It's an incredibly powerful way to design hardware.
So registers are amazing. They can store data and they can shift it, but what happens if you add just a little bit of clever logic, a simple feedback loop? What if you could make a register not just shift, but count? 0, 1, 2, 3. That simple evolution from a register to a counter is the secret that unlocks timers, processors, pretty much everything we think of as modern computing. And that is exactly what we're going to explore next time.